We will take a look at some more two-way tables and probabilities. Hopefully you guys all know standard playing cards. There's four different suits. There's hearts, there's diamonds, there's spades, and there's clubs. And there's 13 of each suit. So that makes a total of 52 cards. Hopefully you do know that, otherwise this problem might be kind of confusing. But I defined two events. The first one is F getting a face card, and the other one is getting a heart. So if we want to design a two-way table, I'm going to start over here and I'm going to say, okay, let's say I do get a heart. And the next one I'm going to say is a non-heart. And I'm going to put the total down here. And the other one I said was a face card, and a face card is King, Queen, Jack, and not face. I'm going to put a total over here. Well, I know that my total amount of cards is 52, and I have to add up to that. And how many total hearts there are, I know there's 13 total hearts. I did that from up here. Face cards, King, Queen, Jack. That means there are three different suits, 4 cards each, so I know that there's a total of 12 face cards, and so I could easily fill out the rest of that chart because I know it has to be 52, and this will be 39. For this I just did 52 minus 13, and this one is really just 52 minus 12. So how many are hearts in a face card? Well, there's one Jack, one Queen, one King that are hearts. So there's 3. So that means there are non-heart face cards. And then when I look at a heart that aren't face cards, where I know that has to be 10, and this one has to be 30. And you could easily check just by looking at all the addition and making sure that your rows and columns add up. So I want the probability of a face card and a heart. So the probability of F and H. So essentially I am going to look where these things overlap. So here's my heart and here's my face, and notice I have a nice intersection right there. So probability it's a face and a heart is 3 different options, and there's a total of 52 cards. So my probability is 0.058. The next says explain why probability of face or heart does not equal the probability of face plus the probability of heart. And the reason why this happens is face cards that are hearts will be double counted because face cards and hearts are not mutually exclusive, meaning they can occur together. Because if you look at the probability of a face card, the probability of a face card is 12 over 52. and the probability of a heart is 13 over 52. But let's go back to number 2 of probability of face and a heart. Notice there's an intersection, and the intersection of face and heart occurs at this 3. And so what happens is that 3 actually gets double counted. So we count that twice. So what happens is we need to take it out once. So the probability of face plus the probability of age, you would just go ahead and add them up. But notice that is very different than probability of face or heart. You got 12 over 52 plus 13 over 52, but what happens is we double counted, so we need to subtract 3 of those cards because otherwise double counting, it's going to change your numbers. And we will definitely do more examples of those. According to NCHS, December 2012, 60% of U.S. households had traditional landlines. Telephone, 89% of households had cell phones, and 51% had both. So let's set up a two-way table. I'm going to start over here. I'm going to say this is landline. This is no landline. So that means over here I have to have cell phone. And this is no cell phone. And alright, they said 89, let's see. They said 60%. Let me get rid of all this stuff up here. 60% had a traditional. So I know that for landline, the total is 0.6. So I know a total of them had 60% had a landline. And then it said 89% of households had a cell phone. So I need a total of 89% had cell phones. And obviously since this is going to be a legitimate probability, this needs to be out of 1. So then you could just go ahead and fill in the rest of these bottoms by just doing some basic subtraction. And then the last piece of clue, they said 51% had both a landline and a cell phone. So that is this intersection point. So I could put a 0.51 there. And then I will compute the rest of the table. 0.51 plus 0.09 is 0.06. So this is what my two-way table looks like. So it says find the probability that the households have at least has at least one of the two types of phones. So we could do this multiple ways. Way number 1 is so we're looking at the probability of the complement of nothing. So that's just 1 minus the probability of nothing. Well, what is the probability that they have absolutely nothing? So no landline and no cell phone will give me 0.02. So 1 minus 0.02 equals 0.98. So there's a 98% chance that they do have one of the two. Another way you could look at this is, let's go ahead and make a Venn diagram. I know my overlapping section is 0.51 from the table. And then since a total of 60% of people, so we're going to call this landline, we'll call this cell phone. If a total of 60% had a landline, but 51% exist in the middle, that means 0.09 has to occur there. And for cell phone, we know a total of 89% have it. So what we're going to do is 0.89 minus 0.51. I know that probably doesn't look like an 8. And that will give you 0.38 there. And so if you look at that, you could just add up all those probabilities. 0.09, 0.51, and 0.38 will give you a total of 0.98. So that means this area outside of the Venn diagram is 0.02. So 0.02 have nothing, and 0.98 all have something. Find the probability that the household has a cell phone. Oh, has only a cell phone. Well, actually, we went ahead and did that. If we know from the table that 89% have cell phones, and we also know 51% have both, what we could go ahead and do is just subtract them. We get 38%, or 0.38, have only a cell phone. And notice we already did that in the Venn diagram there.